I can post this lesson after school just for anybody who's missing and needs to catch up on the homework. I'm going to be recording in this class today. All right, so what is a trend? That word, trend. Let's talk about a trend. I'm going to go to the map that I had pulled up. I think I showed you all the kilometer. I love weather. Like that was in science what I was initially interested in. Did you see, this is temperature. Do you see any trends in the map of the United States of America here with temperatures? Just to give you an idea, this right here, these colors are colder, these colors are hotter. Red and deep red is 90 plus. Go ahead, Jose. Which means the closer to the equator, generally speaking, right? The closer to the equator, the hotter it gets. It actually looks like there's almost a pattern right now that it's like this. But as you go like this, it gets hotter. That is what we call a. And so a trend is being able to look at an area and be like, oh, this is the pattern. As I go down, it gets hotter. As I go up, it gets colder. And that's using the weather just to show a trend. And so you can think of the map of the United States the similar way as the periodic table. The periodic table is going to give us a lot of different trends for elements and how they behave. Welcome back. I was just saying that for anyone who's taking the test next Friday for PSAT, this will only be a few students. Those students would need to take the Unit 2 exam. You can either do it after school next week on Thursday, most likely, or you could take it on the 24th, which would be the next class period. All right, so Unit 2, Lesson 5, periodic trends. So a trend is basically a pattern, looking at the periodic table and drawing patterns. What do we mean by patterns? Well, in the map of the United States, you saw patterns of heat temperature. In the periodic table, we're going to look at patterns such as the size of atoms, such as how likely an atom is to lose or gain electrons, how much like a metal the element is. And so we're going to be looking at trends today. Yes. Yeah, go ahead and grab the pass. So once again, this is the final lesson of the unit, and it is a pretty hefty one because to understand the trends, we're going to have to go through some explanations. I gave you another printed periodic table because you're going to want to write the trends or many of the trends into here as we go along. You will not need, somebody's out right now, sorry. You will not need colors unless you want to use different colors because you're just going to be writing arrows for the trends. You won't have to shade in the whole periodic table this time. But we'll go back to this as we go describe some of the trends. I just have them ready for that. All right, so first thing you need to write, what is the definition and what are the trends we're going to be looking at over today and early next week? So between today and early next week, we're going to be looking at atomic radius, ionic radius, ionization energy, electronegativity, and metallic character. And yes, we're going to define all of those. Some of those I know probably sound like gibberish to you right now. But what are periodic trends? They're simply just patterns. As we look across a row of elements in the periodic table, we call that a period. Or we look down a group, there are patterns that emerge. Patterns in size, patterns in the ability to take additional electrons or lose electrons easily. And so periodic trends, these are patterns we're going to be looking at. So the periodic table, just looking at the periodic table, we can compare elements and we can figure out which element's larger, which element's smaller, which element is more likely to lose or gain electrons. We can actually find out exactly how many electrons each element loses or gains when it forms standard compounds, when it forms its ions, and we're going to figure that out. I'll introduce that today. I'm going to give you some time because you want to both write the definition and what are the trends we're going to be reviewing. So what are the trends you're going to be asked to compare. Looking around to see if you're still writing. Make sure to put down your pencil when you're done so I know, so I can know when I'm moving forward. All right, I see most people have put their pens down at this point, so I'm going to give it a 20-second warning that I'm moving forward. So this is a foundational idea we're going to be working off of throughout many of the topics of today's lesson. And so you need to write it down, and I'm going to fill in a little bit more information after this. Elements are defined as most stable, meaning most unreactive, when they have what we call a full valence shell. This means when their energy level is completely full. So when energy level is full. This happens in a predictable place of the periodic table, actually. It happens when an element has 8 valence electrons specifically, and we often refer to this as the octet rule. Well, what elements have 8 valence electrons naturally? Noble gases. So this actually tells us that elements will lose or gain electrons to have a full valence shell, or to achieve the amount of valence electrons as the nearest noble gas. And so elements will gain or lose electrons to achieve this full valence shell. So you would be looking for the nearest noble gas. For most elements, this is going to be 8 valence electrons that they're looking to have, except for helium and hydrogen, because the first energy level fills at 2. And so you're going to want to write this down, because this is where the idea of how ions form comes from. Because if you'll recall back in Unit 1, we said that ions are atoms that have gained or lost electrons. And today we're going to be going over the factors that contribute to exactly how many electrons are gained or lost by different elements. So by the end of today, or by the end of next class, you'll be able to say, oxygen, I know that that's -2. I know it's always -2, and it should be -2. Magnesium should always be +2. You've seen these numbers in your cell work questions, but it hasn't been explained why the numbers are what they are, and that's what we're going to be going through, and periodic trends help us to understand, because there's going to be several factors that contribute. But ions, we know, are atoms that have gained or lost electrons, and a foundational idea that we're now going over is that elements are stable when they have a full energy level. Meaning, if you have the same amount of valence electrons, if an element has the same amount of valence electrons as its nearest noble gas, then it is defined as stable. And you'll notice when you did the electron configurations for ions, they always pretty much ended up at a noble gas. That's how they naturally. And I think if you did the lab and you did the noble gas configuration, you got most of the elements except for the transition elements would end up being a noble gas, equivalent to the amount of electrons of a noble gas, and that's the ions that naturally form, actually. So this is the rule that's followed there. All right, so I'm giving you some time to write this down, and then we're going to look at the factors that contribute to this and how we can make our predictions of how ions form. So I see most students are done writing. So I'm going to give you about a 20, 30-second heads up that I'm moving forward shortly. So trend number 1. And like I said, there's going to be a few trends we have to look at, and when we look at them in tandem, meaning we look at them combined, it's going to help give us that information to tell us what elements are gaining electrons, what elements are losing electrons, and why. First trend you need to know is one called atomic radius, and the definition for what atomic radius is. Now, the actual definition for atomic radius sounds more complicated than what you really need to know about it. The official definition for atomic radius is 1/2 the distance between the nuclei is multiple nucleus, of two different atoms of the same element when they are joined or they're combined together. And so if you'll recall, radius is 1/2 of the diameter from math. And so really, when we're talking about atomic radius, I want you to think of it as atomic size, which is how large or how small an atom is. And so what we're really talking about here, write the definition, but you also want to have a basic understanding of what's going on. So it's how large or how small an atom is. And it can also be defined as the distance between the nucleus and the outermost energy level, the furthest electron, or the valence electron. So it can also be thought of as the distance between the nucleus and outermost energy level. For that element. Given that information, what the definition is, you may already be able to look at your periodic table and at least draw one trend about the atomic radius. So I'm going to give you some time. Write the definition, and then you should also write down the simplified version of the definition up here. So atomic radius is pretty much the atomic size. This is how large or how small an atom is, and can be thought of as the distance between the center of the atom, which would be the nucleus, and the outermost energy level that holds electrons. Good morning. All right, we started the lesson just a little bit ago. I'll go ahead and update your attendance. I am recording in this class, just so you're aware. atomic radius is the distance between the nucleus and the outermost energy level. Are there any trends that you could already point out looking at a periodic table, just real quick? You don't have to write anything on it yet, but could you compare elements and think about which ones are larger and smaller? Let me specifically ask you, would you think that lithium is a larger atom or cesium? Take a look at lithium, take a look at cesium. Which one do you think would be a larger atom and why?
Cesium.
Cesium. And why?
It's more likely, so it's like bigger.
And that's why we use the Bohr models to help us imagine the electrons on average are farther away if they're in energy level 6 versus energy level 2. So we actually already can draw a trend from that. We know that as we go down the group of the periodic table that atoms will tend to get larger. Don't write it down yet because we'll write down the trends in a little bit, but this is just to give you a heads up. Once we learn the definitions, we'll start to be able to draw some trends. All right, so that's atomic radius, and this is the actual trend. Go ahead and write it down, and I'm going to explain both reasons. That's why you saw some blank slides. This is, you don't have to write down what you see here, but you do want to write this down. What's the trend? Atomic radius decreases from left to right, meaning atoms actually get smaller as you go across the period from left to right, and they get larger as you go down a group. And I'm going to explain both reasons, and you'll, after you write this down, you're going to leave some space to explain both reasons. So atomic radius decreases from left to right, and it increases down a group. I already kind of gave you the preview of down a group. I have to do some extra explanation for across a period. But I'm going to explain both with diagrams. And then after I explain both, we'll mark it on our periodic table as our first trend. Yes. So I'm going to explain both reasons one at a time. The first one, I'm going to start in about 20 seconds, so make sure you're finishing writing this down shortly. Okay, so I left myself some blank slides. Comparing atoms down a group. And let's do something that's not too hard to compare. Let's do sodium, or actually let's do lithium versus potassium. Comparing atoms down a group. If I were to look at lithium, how many energy levels does lithium have? So write lithium first. How many energy levels does lithium have? Filled with electrons. Lithium. Lithium is in row 2,
So it's one
and it should have
What is one?
should have 2 energy levels, right? All right. What about potassium? How many energy levels of electrons does potassium have? I'm not asking for you to fill out the full Bohr model. I'm just asking for you to write how many energy levels. But it's in period 4. On your periodic table, you may want to, on your new periodic table, write down these numbers 1, 2, 3, 4, 5, 6, 7. Because it happened in the bell work at least once, and it's happening in the lesson that you're accidentally skipping hydrogen and helium. That is row 1, that's energy level 1, don't skip it. 1, 2, 3, 4, 5, 6, 7. Potassium has how many energy levels again? It has that means when I'm going back to here, I would actually write 4. Which one's larger, lithium or potassium?
Potassium.
So we would say potassium or K is larger because the main reason, and there's actually a second reason, but because the valence electrons are farther from the nucleus, or you could say the outermost energy level is farthest from the nucleus, and you can write a little arrow for each to see that this is definitely a bigger distance than that is. So as I add more energy levels, my atoms are going to get larger because the electrons are farther away, which means they're taking up more space. So we're okay with comparing atoms down a group? That's a simpler of the two. The second one I'm about to explain. So lithium versus potassium, you want to write which one's larger and why. It's always going to be the element that's farther down the periodic table that's going to be the largest, the one that's lower on the periodic table. You should write these diagrams into your notes so when you're studying, you see these comparisons. It's going to, visuals help to remember part of your group. All right, we're going to take a look at across the period shortly. Across the period is a little bit more complicated, so you'll need to pay careful attention. I'm moving forward in 20 seconds. Comparing atoms across a period. So what is the same? And let's just pick 2 atoms. I'm going to pick energy level 2 because I want it to be as few rings to write as possible. So let's do lithium versus fluorine. So we're going to do the size of lithium versus fluorine. Those are the 2 elements I'm comparing the size of. So in the scenario comparing elements across the period, what's the same that wasn't the same down a group? Which means that the amount of energy levels, so I'm going to write that as a point important thing. The amount of energy levels are the, so that cannot be the factor that we're looking at to figure out the size. The amount of energy levels are the same. So there has to be another factor that is contributing to what the size difference is. If you look at what you wrote down, and textbook says, as I go across the periodic table, atoms get smaller. It says the size decreases, which means that fluorine is predicted to be, and it is smaller than lithium. Why would that possibly be so? What would be the factor? Anybody have an idea? So if we look at lithium, so I'm going to compare it. I'm going to put lithium at the bottom here. Put fluorine here. Fluorine is smaller than lithium. Why? But that seems counterintuitive. It gets heavier. If it gets heavier, why is it getting smaller? Why is it condensed? Okay, so it's condensing.
Wait,
There's something else in the center that's going on.
one of them is a metal and one
It's
of
the
them is a gas.
nucleus. It's the nucleus.
The attraction.
It's the attraction. So here's the deal, and you're gonna wanna write it here. This has 3 protons. Lithium has 3 protons for 2 energy levels of electrons, right? Whereas fluorine has 9 protons, which means for the same amount of energy levels that hold electrons, lithium's nucleus is pulling with a force of positive 3, whereas lithium's nucleus is pulling with a force of positive 9 on its electrons, which actually means that this gets, and you said the word constricted or condensed, right? It becomes more condensed. So if the nucleus is more powerful for the same amount of energy levels, meaning it has a greater force of attraction, the electrons will get closer to the nucleus. And if they get closer to the nucleus, that means that the size actually, it shrinks. That's a good way of putting it. The size shrinks. And so this actually has a fancy name. More protons in the nucleus, it's called nuclear charge. So the force of the nucleus is called nuclear charge. So we're going to say nuclear charge. And that's how positive the nucleus is. Increases across the period. So the factors that contribute that are important here to recognize is that the amount of energy levels are the same. You're not changing the amount of energy levels. So although you have different amounts of electrons from lithium to fluorine, they're contained in the same overall areas of space, in the same overall energy levels. So what happens is, as you go across the period, your nucleus gets more positive because you add more protons, and the more positive your nucleus is, for the same amount of energy levels, the more it shrinks. That's the idea. So this is the tricky rule to remember. So that's why I gave a blank slide to write it down. Write down the diagrams to help you to understand. The trend is across a period, the size gets smaller. As I compare elements across a period, and so fluorine is going to be smaller, and lithium is going to be larger. And so now we're going to go ahead to that periodic table that I gave you today, and we're going to mark it up with the first trend. You can use a pen for this. You do not have to shade in the elements this time. But if you want to use a different color pen or a different shade for different trends, you can. You don't have to. As long as you just label everything properly, it's fine. I'm giving a little bit more time for those who are still writing, about 20 more seconds, and then we're going to continue. All right, so going to our periodic table, the first trend. Atomic size. Go ahead. Yeah, you can grab some. As I go down, the elements get bigger. And from left to right, they go from bigger to smaller. So the best way to memorize this is to draw a diagonal arrow where you point to the largest. And so here we would write increasing atomic radius. Increasing atomic radius. And another way to memorize this is, and this came to me from another teacher. I was attending a meeting with a bunch of chemistry teachers, and somebody brought this up and it stuck with me, so I like to share it. They call it the lower left-hand rule. The lowest element on the left is always the largest, triple L's. Lowest, left, largest. Triple L's. Lowest, left, largest. If you look for the lowest element and you look for be the largest in size. You should draw a diagonal line through the main part of the periodic table. You will not have to concern yourself with F block, but if you really wanted to know F block, they're in between. It would spread this periodic table out farther into 14 groups. But you'll only be assessed on SP and D block elements for trends. Yeah, which is the main section of the periodic table, SPB. All right, so increasing atomic radius, we're looking for the lowest element. That means it's the lowest on the periodic table. We're looking for the element most on the left, and that element will be the largest. And if I was looking for the smallest, I would be looking at the top right corner. It goes from smallest to largest, like this. That's trend number 1. So remember, trends are patterns we can read. The first pattern we can read is the atomic radius, which is also known as the atomic size. The factors that contribute to size include the amount of energy levels, and you should know the factors, at least these two, the amount of energy levels and how positive the nucleus is. And I described both of those factors and what they were as we went through the first trend. Some of these factors will come back into play for some of the other trends. That's why I wanted to bring up what they were. All right, so this, on the top of this periodic table, you should write periodic trends, because you're going to fill in more trends on here. Periodic trends. That's what you're going to write at the top. There are technically 4 trends we can fit on here. There are technically 4 trends we can fit on here. And if you look at the beginning when I said 1, 2, 3, 4, 5. So there's 5 things here. 4 that can fit on that periodic table. 1 that's not going to be on the periodic table that you're just going to have to remember. So the next thing you have to know about is if you want to write, before I go over the second one, I wrote in words here why, what I described, remember with the diagrams a little while ago? I went ahead and I wrote that out here just in case you want. Look at what you've written already and see if you need to add anything in. So the why about across a period, which means left to right. Did you write that the nucleus becomes more positive when you were writing the explanation? This increases the attraction for the electrons that are in the energy levels and pulls the electrons closer to the nucleus, which is why we said that the nucleus gets condensed, or the size of the atom gets condensed. And then down a group, as more energy levels are added, the size of the atom increases. Whatever you didn't already add into your explanations, you should add in now. Check your explanations of across a period and down a group. Make sure you have the important information for the why. I had already explained it, but I just wanted to also have it written out just in case it's more clear here. Then we're going to go to trend number 2. I'm pausing because I still see a decent amount of students writing. I'm going to move forward in about 20 seconds just to give you the heads up. more energy levels are added, the size of the atom increases. So that's the first thing we have said. So now let's take a look at a couple of questions. At least one. Arrange the following elements. See if you can do this. Use your periodic table. Write this in your notes. Arrange the following elements from smallest to largest. This is the type of question you'll see. Look at the elements on the periodic table, so you're going to have to find them. And arrange them from smallest to largest. Barium, helium, nitrogen, copper. Go, I would start by looking for my smallest. Which one is the smallest here? Helium. Because it's at the top right corner. So helium would be the smallest. So I'm going to write an arrow like this. You could write a comma if you want, but you should get used to greater and less than arrows. Helium is smaller than, what's the next one? I've already taken out helium. What's next? Nitrogen. Because remember, we're going from the top right to the bottom left. That's the trend. So helium's here, then the next one's going to be nitrogen. Then the next one's going to be copper, and then the last one's going to be barium. So it's nitrogen, copper, and finally barium. Barium should be the largest. Helium first, barium last. Welcome back. All right,
What if
so
the question was like, which is bigger, boron or silicon?
if you're looking at two opposing trends, you wouldn't. If you're looking at two opposing factors, you would not be able to draw a conclusion. However, I do want to point out that typically the energy level will be the predominant factor. So it's likely that silicon is a little bit because of it being down on energy level. Yes. All right, so the next thing you need to know going into trend number 2. We're about to look at trend number 2, which is also a size trend. But before I can teach you that, there's something you need to know that's really important. And so this is more foundational ideas you need to write. Metals, actually, and there's going to be 2 trends that prove this today. Metals tend to lose electrons and become cations. Nonmetals tend to gain electrons and become anions. So when you look at metals, you should have always seen pretty much in all the examples you've been given with cations that you've been given metals. Mg2+, Na+, Ca2+. Every electron configuration you wrote in the flame test was a metal ion, and every single one was positive because metals lose. Nonmetals tend to gain electrons and form anions. We are actually also going to be able to predict the exact amount that nonmetals will gain and metals will lose, and we actually have enough information to do that now. And so remember that elements gain or lose electrons to attain a full energy level. So ions are formed in order to attain a full energy level of electrons. Last class, I taught you a quick way to look at your periodic table to figure out valence electrons. Now I'm telling you that elements want to have the amount of valence electrons equal to that of their nearest noble gas. And so this is enough information here to now predict what ions every element will make for all S and P block elements. And we're going to go do that now after you write this down. So you're going to go back to your periodic table. I'm giving you a little bit of time to write this first. And we're going to cover pretty much every element except for hydrogen because hydrogen's an exception. We'll explore in a little bit. you're gonna have to memorize your metals and your non-metals for the rest of the class. Because whether an element loses or gains electrons is dependent mainly on whether that element is a metal or a non-metal. And so if you can't tell where your metals are at, then you won't be able to tell if it has a positive or negative charge. You've got to remember where your metals are at and where your non-metals are at. I'm giving about 20 more seconds, and then let's go back to our periodic table, and we can fill in ionic charges for our elements. I had written this earlier, so this is a repeat, but it is that important that I'm repeating it over and over again. But I had written this was written earlier. All right, let's take a look at our periodic table. And what we're going to fill in now is something called ionic charges at the top. For all elements that are in group 1 and 2 and group 13 through 17, for specifically what we call the representative elements, we can figure out the ionic charges for all of those based on the information I presented to you. The first thing to remember is your dividing line between metals and non-metals. Do you remember where that's at? So maybe fill that in for yourself just to remember. Those are your metals versus your non-metals. You should get practice with doing that so you can visualize metals versus non-metals. We're going to start at group 17. Are the elements in group 17 metals or non-metals? Non-metals. So what I've just stated is that non-metals, do they gain or lose electrons? Non-metals gain electrons. And so the next piece, how many do they gain? That's what we're going to fill in now. So how many electrons do the nonmetals in group 17 gain? How would we figure this out? Everything in group 17 has how many valence electrons? 7, right? How many valence electrons does everything in group 17 want to have? 8. So how many electrons need to be gained? What's the charge of every ion in group 17? -1. Does that make sense? Because it has 7, wants 8, needs to gain 1. Electrons are negative. So if it gains 1 negative, it's going to be -1 or 1 minus. That means fluorine as an ion exists as F-1. Chlorine as an ion exists as Cl-1. Always. That's their natural form. All right, group 16. Let's see if we can follow this trend. Group 16, almost all the elements there are non-metals. So they have 6 valence electrons, and how many do they want to have? So how many do they need to gain? And so every element in group 16, when it forms an ion, will be -2. Oxygen is -2. Sulfur is -2. Selenium is -2. This is going to be a trend, isn't it? What about group 15? For the non-metals, at least. -3. We're going to skip 14, and now we're going to go all the way back over here to group 1. What about group 1? Are those metals or non-metals?
There's metals.
Metals. And would it make more sense? They have 1 valence electron, right? 1 valence electron. Would it make more sense for them to gain 7 to become like their nearest noble gas, or to lose the 1 they have, to drop the 1 to go back to the last noble gas? Drop the 1. It also says that metals lose electrons. We're going to learn a little bit more why in a little bit. But that means that every element in group 1 has what charge? The ionic charge would be positive. Because this is 1 plus 1. Every metal in group 2 would then, it follows along, if metals lose electrons, they have 2 valence electrons to lose, what's going to be the charge of every ion formed from group 2 elements? Plus 2. Group 13 is plus 3. We can write it a little bit higher, because we have the space here. And then I'm going to write 14 as plus 4 minus 4. Why am I doing that? Because there's some elements here that are non-metals, specifically carbon, that's really important. And then there's also a decent amount of elements here that are actually metals. So it could be plus 4, it could be minus 4, depending on if it's a metal or a non-metal. And so we can actually figure out the ionic charges, the ions formed for every element that falls in the representative category. Now, we cannot use this for transition metals. Transition metals are more complicated. I told you that last class. When we have to talk about ions for transition metals, which we will in Unit 3, that'll be a discussion for another time. But at least for your main block elements, you can actually predict what ions are going to be formed. So now I know for sure oxygen's going to be what in an ion? When it forms an ion, it's going to be minus 2. Non-metals gain electrons. They gain the amount needed to become like their nearest noble gas, whereas metals lose all their valence electrons. That's the idea. All right, so hopefully you filled that in. You got the idea. This will be went over again. Don't worry, this is the introduction to this idea, but this is also the foundation of Unit 3. Starts there, actually. Go ahead. So this leads us to trend number 2. Trend number 2 is related to trend number 1, but it's not exactly the same. Trend number 2 is called ionic radiance. And you're going to think of this as size of ion. So what is the size of the ion in comparison to the size of the atom? And I have the information here, so you're going to want to write this down first, and then I will explain it like I did for atomic radiance. So it turns out, if electrons are taken away from atoms, that this will decrease their size. Cations are always smaller than the atom they came from. However, when we add electrons, this will actually increase the size of the ion in comparison to the atom they came from. And I'm going to explain why. But this is the trend number 2. Size of the ion versus size of the atom. And I wanted to teach you what the ions were first so that you understand S2 minus, Cl minus, Ar, K plus, Ca2 plus, those are their charges. And if you see the diagram at the bottom, very interesting. Every single one of these different elements has the same amount of electrons, but they all have a different size. They have the same amount of electrons, but they all have a different size. Sulfur 2 minus is the largest. Ca2 plus is the smallest. I'm going to give you some time to write this down, and then we're going to talk more about the second trend. What happened? It's the orange pass. Like I said, today is a full lesson, and the next class we're going to do review activities to help us understand this better. Take a look at it. Sulfur 2 minus, Cl minus, argon, K plus, and Ca2 plus. They all have 18 electrons. So what is causing the size difference in these? So once you get that idea from the first trend, it helps explain pretty much the trends. Once you get the idea, you just have to understand what's being asked for. Sulfur 2 minus, well, that has a nucleus that has a power of positive 16, right? Because it has 16 protons. Chlorine is 17. Argon is 18. Potassium is 19. And calcium is 20. So the greater the nuclear charge, which is the greater the force the nucleus exerts on its electrons, the more constricted the atom will be. Meaning the more condensed, the closer the valence electrons will be to the nucleus. So I'm going to go ahead and I'm going to explain this for each factor, how we can look at this hopefully simply. You don't have to write that diagram. I'm going to write diagram shortly. Just the part in the box. All right. Additional explanation. So the first thing is cation. And just to keep it as simple as possible, I want to compare sodium versus, what is the ion for sodium? Let's practice that. What is the ion for sodium? What is its natural ion it forms? Plus 1, because it's in group 1. So I'm going to compare sodium versus sodium plus 1, specifically, because that's the natural ion that's formed for sodium. So let's compare with 4 models again. How many energy levels does sodium have? How many energy levels does sodium have? Regular sodium. 3. So it would have 3. And how many valence electrons? I'm not filling in everything, but how many valence electrons? Sodium has 1, right? So the explanation is actually quite simple of why sodium plus 1 is going to be much smaller. What does a positive 1 charge mean? What are you doing? Take away electron. That's what that means. And you have to remember that. You're taking away an electron from the sodium atom. Well, what electron are you taking away? The valence electron. The one that's farthest from the nucleus. So instead of having 3 energy levels of electrons, you now have only 2, right? So Na plus 1 has only 2 energy levels with electrons, whereas this has 3 energy levels with electrons. And this definitely means that the cation gets smaller, because the distance between the valence electron and the nucleus has decreased by a lot, because it lost the whole energy level when it lost that valence electron. Are we okay with that? Welcome back. So that is an explanation of why the ion is the positive ion is always smaller than the atom it comes from. What about anions? So that was cation. Now we need additional explanation for anions. And we'll use fluorine. F versus F minus 1. You had hopefully written down that F minus 1 is larger. Anions are larger. So now we have to explain, well, why is that? Why would adding an electron cause an atom to be larger? So fluorine atom, remember, has 9 protons in the center, and it has 2 energy levels, right? 9 protons. So it has 9 protons, and it has how many electrons? Fluorine has 9 protons and 9 electrons as an atom. What about F minus 1? Does the amount of protons change? Still 9 protons, right?
Yes.
But how many electrons do you have?
7.
So in the same amount of energy levels, you have more electrons. What do we know about electrons? Do they repel each other or do they attract each other?
They repel each
So naturally the size would get a little bit larger. So although you have the same amount of energy levels, because you've got more electrons in that second ring, they start to repel. It expands. So because more electrons means more negative charges, the size expands since they repel. You have the same attractive forces, but more electrons given the same amount of energy level, so the size naturally gets larger. And so what you've got to memorize is that cations always are smaller, anions are always larger. And it comes back to some of these key ideas. And so you may also want to remind yourself that when you see -1, this means that an electron has been added. So this is trend number 2. Trend number 2 is the size of the ion versus the size of the atom. Size of a cation is going to be smaller. Size of an anion is going to be larger than the atom it comes from. Giving a little bit more time if you're writing down the diagrams, which you should be, so you have them to look back at. And then we're going to go to the last 2 trends. The last 2 trends are a little bit quicker. And then the one for metallic, I'll talk about more next class because technically you kind of already know it, but I'll make it more clear next class. So cations versus anions. Cations always smaller, anions always larger. Yes. I'm sorry? All right, so you don't have to write this because you already did. This is just a diagram. It'll be posted later on with the lesson that shows the same thing. Lithium plus will be smaller than lithium, and F minus will be larger than fluorine. So just a couple questions, write these down before we go to the last 2 trends. In each pair, determine which is larger. In each pair. Determine which is larger in size. So we're comparing the atomic versus the ionic radius. Calcium versus calcium 2 plus is the first one. Which one would be larger? I'm going to pause to give some time for people to write it down. And then we'll go over it. So calcium or calcium 2 plus, the one that's larger is calcium, because taking electrons away will make it smaller. So the larger one would be the atom, not the ion. And then the second one, N or N3 minus?
N3 minus.
N3. Adding electrons to the same atom, electrons repel each other, so it causes the size to expand. That's the idea. So adding electrons always causes the size to expand. When you take electrons away, it'll cause it to. That's trend number 2. Now we're going to do trend number 3. Trend number 3. Trend number 3. To write down the definition for this one because you've got to memorize it. You've got to memorize all of the definitions for your trends, but this one is really important because if you don't understand what's going on, you're not going to understand the trend. Ionization energy is the energy required to take away an electron, which means to make a cation. Take away an electron, to make something that's positively charged. It is important to note, and I've said this before when we did the electron configuration for cations, valence electrons are the electrons that are removed first. Those are the electrons that are farthest away from the nucleus. So this is a trend we can actually draw from the periodic table. Which elements electrons do you think would be easiest to take away? Which elements electrons do you think would be most difficult to take away? Is there reasoning we could use that we've already went over? I'm going to pause, but you can go ahead and say if you got the idea.
The farther we
The easier or harder it is to get.
easier it is to get.
And that's exactly right. The farther your valence electron is from your nucleus, the easier it would be to take away, right? So you may want to write that down. The farther away an electron is from the nucleus, the less energy required to take it away, because the nucleus doesn't have as strong of a hold. I'm not going to write that part. But it's, the reason is because the nucleus can't hold on to it as well because the electron's further away. So the nuclear force won't be exhibited as closely at an electron that's very far away. So the force will be weaker for electrons that are further away. And because of so if electrons are further away from the nucleus, it will be easier to take them away. Wait, does that mean that this trend is related to another trend that we already learned? The larger the atom, the smaller the ionization energy. And so this actually means it's the inverse trend of size. So if we know the trend for size, the trend for ionization energy is going to be exactly the opposite. I'm going to give you some time, and then we're going to go back to our periodic table, and we're going to mark the trend for ionization energy. Trend number 3. So removing an electron, make sure you've got that. Ionization energy is to make the positive electron. It means to remove an electron. How much energy is required to remove an electron? Electrons that are close to the nucleus are going to be held tightly, bound tightly to the nucleus because the nucleus is attracted. Remember, your key idea is that positives and negatives attract. So it's the force of the nucleus versus the force of whatever is on the outside trying to pull the electron. So let's go ahead and mark it. Let's go to our periodic table that we had written on before. If increasing atomic radius is this direction, then what's increasing ionization energy? We said that the larger an element is, the easier it is to take away an electron. So that means the smaller an element is, the harder it is. And so if energy is the amount of energy required, then the actual trend is exactly the opposite. So you should write an opposing arrow and write increasing ionization energy. Another way to remember this is the smallest atoms have the strongest hold. And so smallest typically equals strongest. So the trend for increasing ionization energy is that it's exactly the opposite of that atomic radius. The smaller the atom is, the more strongly that atom will hold on, the nucleus will hold on to its electrons because they're right next to the nucleus. Whereas if the electrons are very, very far away, it's very hard to hold on. And so that actually tells us that these elements lose electrons quite easily, right? these elements lose electrons quite easily, and these elements don't. Wait a second. That's the last factor. That's called electronegativity, and that's trend number 4. But that actually explains if these don't hold on to electrons very well. That's why they're the elements that have the positive charges. Metals have positive charges because they can lose their electrons quite easily in comparison to non-metals. Yes. Let me check to see if engraving is black. We'll come back. Go ahead, Sarah. All right. So we have one more trend to cover, and that last trend will cover the non-metals and why they have a negative charge. So, trend number 4. I think there's one question to answer for trend number 3 first. Right here. Determine which element has a larger ionization energy by looking at each pair. So does Na or potassium have a larger ionization energy? And what that really means is which one requires more energy to pull electrons. So in the first pair, we're going to be looking for the smaller of the two, right? The smaller of the two will always require more energy. And so it's going to be Na. Na is correct. So we're looking for the highest on the periodic table, and we're looking to the most bright this time. So would aluminum or would chlorine require more energy to pull the electron away? Chlorine. And so that was trend number 3. And so we had 4 to mark up. Yes. To the periodic table? Yeah. Let me pause here for a little bit for those writing, and then I'll go back. And we're actually almost done because the last trend will not take us that long to talk about. And I do have your homework. Your homework is on paper today. It wasn't on paper last class, but it is on paper today. It's for periodic trends. And like I said, next class, we get through everything today. There won't be much of a formal lesson in terms of like me teaching in the front, but you will have activities to help support you to practice periodic trends. And so I'll be explaining what those are after the bell organized class. All right, so ready for the last one? Let me go back first. Let me know when you've got it. I have the periodic table all the way in the beginning. I'll pause until, give me the thumbs up when you've got it written down, okay? The example. After he's done. Yeah, you're good. Wait. Thumbs up when you're done, so I know to go to the other slide. This was the one. Here. You're good? All right, so we've got one more trend to discuss. We have looked at so far today, size of the atom. We've looked at how to figure out what the charge is for an element based on its group of the periodic table, whether it's +1, +2, -1, -2, -3. We've then looked at the size of the ion compared to the atom, and then we've looked at this factor called ionization energy, which is how much energy is required to take an electron away. And so we've got one more thing to look at. And this last trend is called electronegativity. And so it's a big fancy word, but it's a really important trend to remember because this is actually going to be the foundation of polarity. If any of you have heard of polarity before, types of forces of attraction between molecules, it all is dependent on electronegativity. So this is one of those big ideas in chemistry where at this unit, it's just like the tail end of the unit, but it actually forms our understanding of what's going on later on in this class. Electronegativity. This is the actual strength a nucleus has. So the positive, the protons in the nucleus, the strength the nucleus has to attract additional electrons. So just to be clear here, and this is how Cambridge words it, additional additional electrons toward itself. So beyond the electrons it already has, the additional electrons to become like its nearest noble gas. And so every element, this was discovered by Pauling in the 1930s, 1940s. He came up with the scale, and this scale measures it's basically a power index of how much power each element has to pull electrons toward itself. And you'll notice at the top corner, fluorine is the most powerful. And it actually is kind of in this order. The most powerful elements, meaning the ones that can attract electrons, the most are fluorine, oxygen, and nitrogen in that specific order. They're all in period 2 because that's the smallest. Then there are 4.0, 3.5, and 3.0. Fluorine's really close to nitrogen. It's also 3.0, but we memorize it as Fa. These are the most powerful elements. This means that these elements are more likely than any other element to attract electrons to themselves. So there's a couple points to make here. Make sure you've written the definition. Why is fluorine so powerful?
So small.
Very small. It has 7 valence electrons that it wants to have 8, right? So it's very small, and its nucleus has a lot of power to attract additional electrons. So the idea is the smaller the stronger. The smaller an atom is, the stronger it will be to pull electrons toward itself. Okay, there's another thing that's really interesting here. Most noble gases don't have electronegativity, so noble gases are not included in this trend. And you're going to want to write that down. Noble gases are not included in this trend. Why not? This is the only trend they're not included in.
Because they cancel out. Because they are.
Right. So if the idea of electronegativity, the definition is that it's the strength the nucleus has to attract additional electrons. Do noble gases want additional electrons? If a noble gas gains an additional electron, it becomes like these elements and it becomes less stable. It loses stability. And so no, noble gases do not want to gain additional electrons. They want to stay just where they're at. That's why they're chemically unreactive, actually. And so noble gases are specifically not included in the trend for electronegativity. That's why I said you may want to go ahead and memorize the most powerful elements in this order are Fa, F-O-N. This is going to be important because when you learn about a concept called hydrogen bonding, which you might have heard of in biology, if you recall from biology, hydrogen bonding actually also incorporates the 3 most electronegative elements of hydrogen when they're bonded and connected to hydrogen. We're going to learn about that at the tail end of the unit theory, the beginning of the unit. Because they're connected to oxygen and hydrogen, it gives a large difference in electronegativity, and because of that large difference in electronegativity, it causes a greater polarity than normal, which gives water special properties. But there are other compounds like water, like alcohol and ammonia, that also have hydrogen bonding. And it is when you have hydrogen with the most powerful elements in their electronegativity. And so this is a key factor, and it goes back to explain what I said at the beginning. What I said at the beginning is that metals lose electrons and that non-metals gain electrons. Now, why do non-metals gain electrons? Can we explain why? Because they have high electronegativity. They have high power. Their nucleus has a great amount of power that it can attract additional electrons. And so it is due to the high electronegativity of non-metals that they have negative charges. And so it helps explain what's going on. So we're going to go back to the periodic table one more time to mark that final trend. Let's go mark our final trend, which is electronegativity. And you can actually just put here increasing ionization, increasing electronegativity. And then what do we know about electronegativity? Noble gases are not included for electronegativity. So for electronegativity later on in this class, when it gets brought up again in Unit 3, we're going to use the letters EN to describe electronegativity, lowercase e, capital N, instead of writing all of those letters. There's one more trend that I at least want to bring up, just in case there's some questions in the homework that are about it, that I just want you to fill in real quick. The last trend that was brought up in the initial part of the lesson was metallic character. What do you think metallic character means? Metallic character. Because there was one other trend here that said metallic character. What does that mean? How much like a metal it is. That's all that is. Metallic character is just how much like a metal an element is. Can you look at these arrows? Which one do you think is the one for metallic character? Do you think elements are more like metals going this way? Or do you think elements are more like metals going this way? Do you think it's diagonal top to bottom or diagonal bottom to top? Do you think these are most like metals?
No, the other way.
It's this way. So next to increasing atomic radius, just write for yourself so you can answer the question. This is also increasing metallic character because it actually exists on a spectrum where you start with nonmetals, then you have your metalloids, then you have your metals. So with increasing atomic radius is increasing metallic character. More like a metal, more likely to lose electrons, and more likely to have the properties of metals. So that's actually it for the content of Unit 2. Periodic trends is the last topic for Unit 2. So I'm going to pass out the homework, and I told you next class after the bell work, we're going to do some review activities with this for sure to help you further understand this topic. So, the homework, if you want to, you can get started within the last 10 minutes of class, or you can take a small break later. We talked about electronegativity. I'll go back to that in a minute. Let me pass out the homework first. Here we go. Here we go. There we go. Now that I've dumped a bunch of information in your brain. Here we go.
What? This is higher class, 30,000.
All right, so remember, you can get started with the homework, or you can take a quiet brain break to the end of class. I know that I filled your brain with a lot of information today. Sarah, you want me to go through the activity? Yeah. Did you get a picture of this? The rest of what I filled in? Yeah, I filled in metallic character and electronegativity.
Oh, okay.
I check my own needs. I check my own needs. What do you have?